Okay. Let's keep going with linear regression. So today we're going to first finish up linear regression. And this is a sort of, as I said, kind of an introductory unit on machine learning. And linear regression is one of the simplest algorithms, which I guess you could call a machine learning algorithm. And so we're going to finish that up, again, motivated by this example of predicting the peak demand given something like temperature, given some external features like temperature. We'll finish that up today, and particularly we'll go through the derivation of linear regression as a optimization problem. A lot of people may have seen linear regression before, but you may have seen it like as a projection onto a line and things like this. And in this class, we're going to focus a lot on optimization, so it's really important to understand linear regression as an example of an optimization problem. And then after that, we'll cover an overview of linear algebra and some matrix calculus. That's all we'll get to today. It's going to be the first of 2 review sessions. The next one will be a review as well on Matlab and some optimization. But today, we'll hopefully get through as much as we can of linear algebra and maybe get to some matrix calculus as well. If we don't finish this up today, it's fine. We can just keep going next time. I do want to kind of take this one in some detail and describe linear regression in some detail. So first of all, are there any questions from last time? We're sort of picking up in the middle, and I'll try to recap some of our notation. But were there any kind of general questions from last time? The problem setup and kind of the general problem of building a model that can predict future peak demand. That all made sense? All right, great. So let me just put sort of the formal definition of what we're trying to do here. So remember, and I'll just write a couple things here. I won't write out all the notation. It's in the previous slides there. But we had some prediction. We're making y hat I. That's going to be the predicted demand, peak demand for the ith example in our data set. That's going to be equal to our parameters theta, which is a vector in Rk, has k different entries here, times some features of the ith input example. So xi here is a vector. I mean, in theory, it's a vector. Here's just one number. It's the input, which is in our case the high temperature for that day. Phi here is some features that we construct from it. In the simplest case, it's just we just take that one element and append a constant term to it. We'll shortly talk about other types of features you can make for these things. But we have a simple scenario like this, and we want to make our predictions in some sense close to the true values yi. We want this to approximately equal the true output yi. That's our goal, right? And you remember, we're going to measure this closeness here by a loss function, which we're calling L. And in particular, we're going to use the squared loss. Right? So in this case, our cost function, which we denote J, and again, we're thinking about our cost function as a function of the parameters we pick. It's also, of course, a function of the true outputs, the inputs, everything like that. But we can't choose those. Those are given to us by the data. So we're going to think of our cost function J of theta being equal to just the sum over all our examples. Remember, there are m different examples of the loss between our predicted output and the true output, which in this case is equal to the sum from I equals 1 to m of theta transpose phi of xi. This, remember, is our predicted value minus yi squared. So we're trying to do that. And in particular, we want to pick the parameters that make this thing as small as possible. This is an example of an optimization problem. We are optimizing over theta to minimize this function here. Question, of course, is how do we do that? How do you find the theta that minimizes that? And can we do it? You wouldn't want to guess all possible thetas, right? Maybe in this case, theta would be 2-dimensional, so you could search over a lot of them, but that's going to get pretty cumbersome pretty quickly. So is there a faster way to actually find the good theta there? Before doing that, though, I want to write this expression here a little bit more compactly. And actually, I'm going to write it in matrix notation. And actually, writing things in matrix notation like this is one of kind of the key elements of a lot of the actual linear algebra we do in this course. It's not so much about complex linear algebra manipulations, but there will be some skill involved in actually converting things like this into simpler expressions. So the first thing we're going to do, as I say, is going to convert this to matrix form. And that will actually help us come up with a way of optimizing it a little bit more directly, or a little bit more intuitively, I guess. So I'm going to define a few matrices here. First of all, I'm going to define a matrix big phi, which has the phis for every different example in its rows. All right, so big phi here is a big matrix. It's a matrix in R. Remember, there are m different examples, so it's going to be in R. It's going to have m rows and k columns, because each row is going to be a set of features. And that'll be equal to, as I have written up there, for example, x1 transpose is the first row. By definition, right, we're thinking of vectors as being column vectors. And so if we want a row vector, we need to transpose that element. So we're going to define a great big matrix like that with all of our features. And next, we're going to do the same thing for the y's. We're going to define a vector y in Rm to be equal to all the different yi's. And I should say this goes down, of course, to phi xm transpose. Right? We're going to do the same with y, to ym. I'm just repeating what's on the board or on the slides. Sometimes it's helpful to write it and have it on the slides. So now I want to make a claim. And it's oftentimes easier to deduce these claims after the fact rather than sort of derive them in the first place. But I'm going to claim that j of theta is equal to this term here. It is equal to, maybe I'll write it here. This is equal to the L2 norm. An L2 norm is just defined like this. The L2 norm of a vector z is equal to the square root of the sum from I equals 1 to n. Z here is an Rn, we'll say. 1 to n of zi squared. And so the actual squared L2 norm is just the sum of the elements squared. So this notation here just means we take each element. Oh yeah, we can close the door, actually. It's getting kind of loud out there. This notation here just means we take each element of z, we square it, and we add it all up. This also equals, by the way, z transpose z. It's the inner product of z with itself. We'll cover this a little more detail in the notation section coming up in the linear algebra. But I'll just say this for now as something to take as being true. So I'm going to claim now that this sum here can be represented like this. Phi times theta minus y. The 2 norm of all that. OK, so first of all, is that obvious to people? As a raise of hands, who finds that transformation there obvious? OK, so maybe a couple. So let me go through why it's the case. OK? I'm going to erase these ones, but they're still up there. We want to show this equivalence here. So remember, phi is a vector in m by k. Theta is a vector in rk. So first of all, this multiplication makes sense, right? Because the number of rows, columns here equals the number of rows of theta. And what is this vector here, though? What this is a vector where the first entry, for example, would be the first row of phi times theta. It would be that inner product. So the first element here would be phi x1 transpose theta. The second element of this vector here would be phi x2 transpose theta. And by the way, it doesn't matter if you do theta transpose x, theta transpose phi or phi transpose theta. That's the same thing, of course. You can reverse that. And this is all the way up to phi xm transpose theta. OK? So that's what this vector is here. This is a vector, remember, because this is m by k, and this is k by 1. So the product, it has dimension m by 1. Now we're going to subtract y from this whole thing. So that's minus this big matrix of y's here, y1 to ym. But of course, those are two matrices of the same size, two vectors of the same size. So we'll just put this in the same vector here. So this whole thing, maybe I'll write it like this. Phi theta minus y equals this minus y1 minus y2, etc., minus ym. Okay? And hopefully now it's apparent that this vector here just contains all the terms in this sum. Right? Every term, every row here is just one term in this sum of this vector. So now if we take the 2 norm of this vector and square it, that is just every element here squared, added all together. And that's exactly the definition of the 2 norm squared. Now, it's oftentimes a lot easier to go from this expression to this one than vice versa, right? You have to be a little bit familiar with matrix notation in order to go from this one to this one, to just sort of see intuitively that, of course, you can write this like that. But just by the definitions of matrix multiplication and the definitions of this 2 norm here, you should be able to take this and infer that it's that. Right? So at least at first, it might be easier to go through it in that order rather than the other order. But you'll need to do a little bit of both of these in this course. So it's the one kind of trick with linear algebra, or not trick, it's the one kind of skill with linear algebra that we will use. But the good news is that beyond this, the actual manipulations you do are not very complex. So now let's get a little bit more complicated even. And let's talk about optimizing this. So our problem here, right, is minimize over theta of j of theta. So how do we find the minimum value? How do we find the parameter that minimizes a function? Let's look at it first in 2D. Sorry, 1D, I guess. 2D if you include the inputs. So the input here, theta, theta will assume to be a scalar. So we have a one-dimensional parameter we're trying to optimize over. And our function here is just some quadratic term. It's j of theta equals, say, theta squared minus 2 theta minus 1. Well, how do we find the theta that minimizes this? I'm plotting this function right here. And the minimum value just happens to be 1 here. Or sorry, not the minimum value. The value of theta that minimizes this thing is 1 here. But how do we actually find that? So if you remember kind of basic calculus, the way you find a minimum of a function has a minimum like this if its derivative is 0. Right? The derivative of the function is the function's slope. And so when the function is in fact kind of an upward curving function like this, and we'll mainly be dealing with upward curving functions for a lot of this class. We'll go into a little bit more detail about what that means exactly, but just take my word for it that this function, for example, is kind of an upward curving one also. But in that case, the point where the derivative is equal to 0, this is the minimum, or this is the value of theta that achieves that minimum. Right? Where the slope is 0. And the way you find the slope is just compute the derivative of this function. So the derivative with respect to theta, the derivative of j with respect to theta, in this case, I don't know how to do this, right? It's just you take the 2 here. So it's 2 theta minus 2. And if you plot this function, what you'll see is it crosses 0 exactly where we would expect, right? It crosses 0 at the point 1, which is the minimum value of theta. And so to find the optimal value of theta, a little more rigorously, what we can do is we can take the derivative and look for the point where that thing is equal to 0. So we set this expression here equal to 0. And I'm writing theta star here because theta star signifies the optimal value of theta. So really what's the case is that at the optimal value of theta, this equation here holds. And so what we have in the end is theta star equals 1. So high level, to optimize a function, you take its derivative, set the derivative equal to 0, and solve for that derivative. Solve for the theta that makes that derivative equal to 0. Now, it's going to be the exact same procedure in higher dimensions here. It's a little bit harder to find, not find, but it's a little harder to think about these derivatives sometimes because they're multivariate derivatives. But it's this exact same procedure. It's really simple. So let's go through that. And I should add, this is probably on the level of, maybe not quite, but about the most complex math we'll do over the entire semester. I like to sort of front load it a little bit because it does look a little bit daunting at first. And you know, you should get familiar with this kind of stuff quickly because we'll sort of keep at this level. But don't worry if it looks a little bit daunting at first. We'll have this review afterwards. I want to start with kind of the practical problem. We'll have this review then. And there's also some notes online explaining a lot of this. So it isn't actually that tricky. It just takes a little bit of time getting used to the notation. So now let's talk about the multivariate extension of a derivative. Because that's what we need, right? When we have a function of many inputs, we somehow want all the derivatives to be equal to 0. And the first type of derivative we'll talk about in this class, so there are other kinds as well, there's other names for these things in multi-dimensions, something called the gradient. The gradient of a function, for a function j, I'm going to erase this. Is that okay if everyone sort of have this basic stuff here? Okay. So for a function j, and now I will let j be some arbitrary function taking vectors in Rk as input and producing a scalar value. It's important to note that we're taking j is a vector input and scalar output function. Okay? And in fact, it doesn't make any sense for j to be, say, a vector valued function, because then what does it mean to minimize it, right? Then it has different values. Which one do you want to minimize? When we talk about minimizing things, we're going to talk about scalar valued functions. Then minimizing makes sense, right? We want to minimize this one output value. And we have k input values. And the generalized condition for setting the derivative equal to 0 is something called the gradient. Theta will minimize j. This is assuming j is smooth and things like this. We won't worry too much about these conditions here. We're going to assume it's differentiable. We can take all these derivatives, all these things like that. But if we can take our derivatives properly and everything kind of works like this, then the condition for theta to minimize j is for this thing called a gradient, which we're going to denote a little triangle with respect to theta of j of theta. This thing evaluated at theta star. So this notation here means we're going to take this gradient here and evaluate it at the value of theta star. This has to be equal to 0. That's just a generalized condition of what we wrote before, where this gradient is defined as follows. The gradient of j of theta with respect to theta is equal to just a vector of all the different partial derivatives, right? It's sort of exactly what you would think it is. You just take the derivative of j with respect to each different input. So the first element, and we use the notation here, little script d rather than sort of normal lowercase d. This is called a partial derivative here. Just to denote essentially the fact that j depends on other things rather than just theta k, for example, here. But we're going to think of these things just as the derivative with respect to that one term. Don't worry about that. You can just, it's all very, very simple, really. So the first element here is just the derivative with respect to j of the first element theta 1. That's the first element in the gradient. The second element is just the derivative with respect to theta 2. We'll go through an example actually in the linear algebra review. Here I'm just sort of giving the formal definition. All the way down to the derivative of j with respect to theta k. Okay? But the important part here is that this thing is itself a vector, and it's a vector in Rk. So So it is a k-dimensional vector itself. J takes k-dimensional inputs. This thing produces k-dimensional outputs. And I'll give a few examples of important gradients here, important rules or important specific gradients. The first one is that this gradient is what's called a linear function. All that means in this context is that if we take the gradient of two different functions and multiply them, add them up and multiply them by some scalar number, we essentially can pull the scalars in the addition outside of the gradient operation. So the gradient of a times f of theta plus b times g of theta is equal to a times the gradient of f of theta plus b times the gradient of g of theta. So we can basically push gradients inside addition and inside multiplication by a scalar. This is the exact same, by the way, as normal derivatives. Now, if you have the derivative with respect to x of x squared plus 3x, right, you can take the derivative of each of these separately and add them up together. Two other important rules for gradients that we're going to use are these two. This is a formula for the gradient of what's called a quadratic form and a inner product here. So remember, what we're saying here is we're saying j of theta could be equal to, for example, theta transpose a transpose theta. Sorry, theta transpose a times theta. And where a here is a matrix in R k by k. And what this is saying is that the gradient of this thing, gradient theta, j of theta, is equal to a plus a transpose times theta. And the thing to keep in mind here is this is sort of like a vector case of j of theta being equal to a times theta squared if theta was a scalar value. And the derivative of this would, of course, just be derivative of j of theta would, of course, just be 2a theta. And you have this sort of same thing. It's just that you're actually transposing it. So you have two a's here times theta. Since they're matrices, you actually have to transpose them. By the way, the way you come up with that is you just plug in these definitions and take the derivatives element by element. I won't do this one. This one's actually in those notes I posted online, so it's there if you want to take a look at it. But let's do this next one. So let's do this one because it's really, really simple, right? So let's say that here j of theta equals b transpose theta, or b is some vector in Rk. So the first thing to check is that is this a valid function of that form, right? It is, because it takes as inputs vectors in Rk, because we need to have theta be a vector in Rk in order to transpose it and multiply it by b transpose. Sorry, to multiply it by b transpose. And it outputs a scalar value, because what it's outputting is the inner product between b and theta. So let's take an example now. What is the derivative with respect to this thing, b transpose theta? Sorry, derivative of this thing with respect to theta 1. Well, remember, this inner product here has a really simple form. This is just equal to the sum from I equals 1 to k of bi times theta I. Right? So let's look at all the terms that have theta 1 in them. Because the rest are just constants with respect to theta 1, right? The rest when we take this derivative, it'll just be constant. The only term that has theta 1 in it here would be the corresponding b1 term here. So this partial derivative here is just going to be equal to b1. Sorry, b1. And similarly, you can think of it pretty easily that this thing with respect to any I is equal to just bi. Right? That's the only term. Only one term has a theta I, I shouldn't write it like this because now I'm summing over I. I'll use a different index here maybe. To keep things a little clearer, I'll talk about theta j and bj. And the only term here that has theta j in it will be the term that's multiplying by b sub j. And so the partial derivative here is going to be b sub j. And hopefully now it's fairly obvious from this that if we just look at this fact here and look at the definition of the gradient, this thing, the gradient of theta, I'll write this b transpose theta, let's just equal to a big matrix where the first one is b1, second one's going to be b2, all the way to bk. Now that's just b, right? It's a very simple gradient, naturally. But that's how you compute them. You literally just go through, see what each derivative is here, and then write out the corresponding element of that matrix, or that vector. This one's a little trickier, but if you want to go through it, give it a shot and see if you can derive that. All right, so now we're equipped with our rules for gradients, a couple of them at least, and we're ready to solve that problem. And this is only one more step now. We're ready to minimize. Everyone have this stuff here? Okay. I guess one disadvantage of video recording is that I do tend to erase a lot, as I said, but hopefully if you need it again, you can watch it back on the video. So now, what we want to do is we want to minimize over theta of this thing. Theta, or sorry, over theta, phi times theta minus y squared. So let's write this out in a little bit more detail, apply our rules that we have for gradients, and that will actually give us the solution to this problem. So first of all, let's do the first thing first. Let's make this a little bit simpler for us to apply our rules to. You could actually come up with rules pretty quickly that apply directly to this, but let's just go with the exact form we have. So j of theta equals this thing, phi theta minus y. And remember, for any vector z, this norm squared is just equal to z transpose z. So let's just write this out a little bit more explicitly here. This is actually now phi theta minus y transpose phi theta minus y. Which, now let's just distribute out the different terms here. This is going to be equal to, well, everyone knows that, right, when you transpose a product, A times B transpose equals B transpose A. So we're going to transpose this thing first, but what we get, sorry, B transpose A transpose. What we get here is we get theta transpose phi transpose, I'm just taking these two terms here, times phi theta. Erase this. Minus, well, let's take this one here. We have y transpose phi theta. Now let's look for this one times that one. That's another theta transpose phi transpose y plus, because we have two negatives here, y transpose y. Okay, so I've just distributed this product out into each of its four different parts. And secondly, I'll just simplify this a little bit more. Because this thing here, this is just y transpose this vector. This is the vector transpose times y. Those are the same thing, of course. So you can just actually only have one of these two terms, which is going to be minus 2y transpose phi theta. Okay, that's just what's on the board there. All right, so then this is our new expression for j of theta, which is a little bit easier to manipulate than just the norm itself. But we've just used a definition, really. And now let's take the gradient. Let's use our rules, because now everything we actually have is in one of those, as you'll see, is in one of those forms that we can apply rules to. So let's take the gradient with respect to theta of j of theta. We'll do it in this form. So remember, first of all, we can distribute out the gradient to each of these terms. So it's going to be equal to the gradient with respect to theta of theta transpose phi transpose phi theta minus the gradient with respect to theta of, actually I'll just move the 2 out immediately. We can remember move constants outside of those things. Y transpose phi theta plus the gradient with respect to theta of y transpose y. Okay, so let's now just use our rules. This term here is theta transpose something here transpose times theta, which is, if you look back at our rules, just in this form. So the gradient there is going to be this matrix A, and here this thing is A here, plus A transpose times theta. So it'll be this thing, phi transpose phi plus phi transpose phi transpose all times theta. But I'll actually go and even simplify again here, because phi transpose phi is, and you can check this pretty easily, is a symmetric matrix, meaning it's equal to its transpose. If remember, you have rules for transposing a product there, so you transpose this one and transpose that one again, it just ends up being the exact same thing. So this is actually just equal to 2 phi transpose phi times theta. Okay, and the same for this next one. Let's use our rules again here. Minus 2 times this gradient. Well, you can think of this term here as being our B transpose from before. And remember, the gradient of B transpose theta is just B, so the gradient here is going to be really the transpose of this term here. So it's going to be phi transpose y. And finally, this term does not have a theta, so the gradient with respect to theta is just 0. Okay, so here's our gradient. The last step now is knowing that this thing will be equal to 0 at the solution, at theta star. So all we do is we say, okay, well, 2 theta transpose theta, sorry, phi transpose phi times theta, minus 2, I'll actually write theta star here, because indicating that this is holding for the optimal theta, minus 2 phi transpose y equals 0. We are going to set this thing equal to 0. And now we solve for the theta that actually makes that equal to 0. And in this case, that would just be, well, we move this over to the other side. So we write this as, let's actually first just divide by 2, get rid of these 2's here. Then we have theta, phi transpose phi times theta star equals phi transpose y. And now using, remember, you can't just divide by this. This is a matrix here, a scalar value. But the equivalent thing is multiplying by the inverse. So this is equal to, this is the same thing as saying theta star equals phi transpose phi inverse phi transpose y. Okay, we're done. That's it, I promise, for today at least, in terms of the math. So big picture, let's step back what we did. It's because it's really very simple. What we did was we took our expression, our cost function, which is a function of theta, something we wanted to minimize. We took its gradient, its multidimensional derivative. We set that equal to 0. Remember, that's the whole vector that has to be equal to 0. And then we solve for what theta will actually give us that thing being equal to 0. That is the optimal theta. That is the minimizing value of theta for this function. And that is the best theta we can find. This term here is actually so common. There's a special name for it. It's called the normal equations. It's one of the most standard kind of forms of one of the most standard uses of linear algebra will be to compute a least squares solution like this. And in fact, there's lots of different ways of deriving this exact same thing. You may have seen a similar derivation about projecting the points onto a lower dimensional subspace, actually projecting them onto a line. You can derive it all that way. That certainly works. You might have seen these defined as things like projections and stuff like that. That's all completely a way of doing it. But I think that in this class, we're going to use this paradigm of optimization a lot. And so it's very helpful to see how this comes about via an optimization problem. All right, so didn't take us too long. Are there any questions about this? Who here has seen this before, actually? Had gone through that derivation before? OK. So hope there are no questions. If there are, please come talk. As I said, this is not going to be this is representative of some of the harder material that we actually use in this course, especially if you have not seen it before. So if you can get through this and understand this, you'll do fine. But it is important to get this and understand what we're doing here. All right, and now since this class is really about not just the math, but actually also coding it, let's see how to do this in Matlab. OK? So we want to write code that will actually solve this thing that we wrote right there and give us the theta that actually does this. And I think actually, I didn't include a graph on this slide, but I have a graph on later slides. So I'll actually, in the lecture after today, I'll go through the actual Matlab code and you can see what it looks like. But anyway, remember what this looks like is this. Actually, I have the graph. It's just from old data. So what it is remember, we have all our inputs here. We have our outputs. And this theta that we've learned from our equation here, this is actually a graphical representation of it. So I said before that our model was theta 1 equals this thing and theta 2 equals that. And the way I actually got those numbers was I just computed that equation. And this is the Matlab code I used to actually compute that. First of all, there's some sort of bookkeeping, right? You have to load your input variables in. You load your output variables in. So x's, you load some file called high-temperature.txt. In reality, you probably wouldn't necessarily be supplied this directly. You have to go create this somehow. But we'll assume it's given to you. The second line there, y, we load the output, which in this case is peak demand for the different days. We set up some sizes. So the m, remember, is the size of the number of examples we have. So that's the number of rows in the X matrix. And we construct our feature vector, or rather our feature matrix phi, which has in its first column just the actual values of x, and its second column the values of y. Or sorry, second column the values of 1. Remember, our feature vector here is just equal, in this case, to x1, xi1. Right, so that means big phi is going to have all the x's, x1, x2, xm, as the first column, and just all 1s in the second column. That's what I'm doing in that fifth line there. Then finally, I'm all set. We're all done. We can just actually compute this expression here, which we can write as the inverse of phi transpose times phi transpose times y. You should not actually write it like this, though. For technical reasons, it's actually Matlab, this is such a common operation that Matlab has a special operation for it, which is the backslash operator. So if you type theta equals phi backslash y, that gives you the same expression here, gives you the same exact solution. And in fact, it computes it much more efficiently. We won't go into quite why this is, but the short story is that actually computing an inverse is not the most efficient way of solving an equation like this. It's actually a little bit better to leave it in this form like this and kind of just solve it as we did actually that. No, we didn't do this yet. To solve it basically using, as you would any set of linear equations. We solve for some variables and substitute for other ones back in there, which is exactly what a computer does. But the short story is that this is a rather large matrix you have to form and invert. And actually, you can do it more efficiently if you're just trying to solve for a particular value of theta, and much more numerically robustly, too. So this typically gives more accurate solutions up to, say, machine precision, whereas this could introduce a little bit more error. That's all we're going to cover about numerical linear algebra here. You don't have to actually worry about what's going on behind that, but it's just might be good to know that this one's slightly more efficient than this. So it's really what we're talking about here is, I guess depending on how you count characters, 1 character in Matlab, or maybe 3, 2 variables and a backslash. And this is kind of why we use Matlab, right? It's very, very easy to code these things up. And so you can very quickly run linear regression. Whereas if you're writing, say, in C or Java, it sometimes can be, you have to write a whole framework of code before you can even solve this problem. And of course, that code exists out there, but you have to become familiar with it. And so it tends to be pretty easy to use Matlab for these kind of things. So that's the first bit of our class today. Actually, again, are there any questions about any of this? All right, so I wanted to do this part first rather than start off with the review of linear algebra, because I want to sort of illustrate what this is actually used for. Right? In the context of energy in the smart grid, which is what this class is about, why are we sort of spending all this time on linear algebra? Well, a lot of problems are solved by creating very simple, say, least squares models of these things, of input-output relationships. We're showing one example here where you predict peak demand from high temperature, but you can imagine we're going to do a lot more of those things. Predicting maybe how much wind power there's going to be, predicting maybe what's going on inside a house, what devices are being used. These are all slightly different problems, but they all use very similar frameworks, actually. Not all least squares, but we'll quickly, after we finish the review, talk about slightly more general context that essentially use the same framework. Very little will change, and you'll have very powerful algorithms, like if you've ever heard of support vector machines, or support vector regression, or any of these kind of things. These are actually all essentially the same framework, just slightly different optimization problems is the only difference. So it's a really very, very powerful kind of framework for thinking about problems, this optimization framework. So having said that, what we're going to do now is we're going to take a little break, though, or switch gears a little bit, and just give a little bit of a review of linear algebra. This is clearly sort of a very important core topic for a lot of this, and given that it was not, the prerequisites for this course are some linear algebra experience, but not maybe expert, not necessarily being an expert in linear algebra, I want to go through a little bit of what we're going to use here in the course, and just familiarize yourselves with basic notation, basic ways of transforming between functional forms like this and vector forms, and just so you have some intuition about how these things work. Hopefully, the introduction here already gave you a little bit of intuition about the notation we're going to use, but I want to kind of put it in one source, and certainly as a set of slides, I want to have one set of slides so you can just go back and refer to this rather than having to find it scattered throughout all the different lecture slides. So let's switch gears now. Where am I? Here we go. All right, so now let's start something entirely different and start our linear algebra review. Most of this, hopefully, will be familiar to you already. As I said, linear algebra, or basics of linear algebra, is a prerequisite for this course technically. So hopefully everyone here has some familiarity with this, but maybe certain notation you haven't seen before, or certain sort of uses or functions you haven't seen before, and so that's what this set of slides is for. I'm going to go through fairly quickly. So I'm going to kind of go pretty fast through all this because it should be review, but please do interrupt and stop me if you have any questions during this time. So the basic here, I think I've already said this in words several times now, but we're going to use extensively linear algebra here. And these lectures really are a single source for all this review that we're going to use in class. And hopefully, and we're going to cover some advanced material too, like this matrix calculus stuff that we had some introduction to today. But that will go a little bit slower when we get to that part. And I should also say, we will present the methods again when we use them in class. So we'll talk about other things like second derivatives for vector valued or for vector functions, which are called the Hessian, or gradients of, not gradients, but derivatives of vector valued functions. So if they have vector outputs, what's the equivalent term for the derivative there? We'll talk about all these here, but we'll review them again in the notes when we're actually going to use them for a certain topic. It's just I want to have a single source for all of these. So the more advanced topics we will see again. They're just meant to be here to kind of have it all in one place. So first of all, linear algebra is about the study of linear equations, right? This is sort of obvious, but oftentimes actually it is not said when people are first studying linear algebra. So linear algebra fundamentally is going to be about equations like this, linear equations, sets of linear equations. So here we have two linear equations and two unknowns. All right, two equations, these two, and then two unknowns, x1 and x2. And now you probably learned that assuming this is not sort of a degenerate set of equations, you can actually solve for what x1 and x2 are. That ends up being equivalent to an inverse, but forgetting about that for now. The point of linear algebra, in some sense, is that we can write this. It gets kind of cumbersome to write this, right? Maybe for two equations, two unknowns, it's fine. If you have 100 equations, 100 unknowns, writing them all out term by term would get pretty tedious pretty quickly. And so really, in some sense, linear algebra is just a set of notation that lets us write things like this very quickly. So in particular, we can write this equation like this as ax equals b, where the rows of A correspond to the coefficients of those linear equations. 4 and -5 there, -2 and 3. X is just going to be the vector containing the values of x. And b has the values on the right-hand side up there. So this equation here is just shorthand. Ax equals b. It's just shorthand with these values. Is shorthand for those sets of equations up there. And you can do things like solve for it, manipulate them all using this kind of form. So for example, what is the x that solves this? Well, it would just be A inverse times b. That's much easier than trying to think about exactly, how we substitute correctly and solve that equation kind of term by term. And by the way, when a computer actually, we can say something like this, right? Ax equals A inverse b. Isn't really saying anything, right? It's not saying how we actually compute that. For a computer to compute that, it does it almost exactly like you learned how to solve those things. It multiplies them by certain terms, adds them up to cancel out other terms and things like this, and then substitutes back in the old equations to find the other solutions. The computer is doing that exactly. It's just doing it in an algorithmic way. So we're going to kind of work on this level in this class. We're not going to worry about how the computer is actually finding A inverse or solving this equation. But it's important to know that this notation here really is referring to solving equations like this. All right, so now let's look at some basic notation. I've been using this already in class, so hopefully this is pretty familiar with everyone. But we will denote a matrix with m rows and n columns as A in, this sign means in, R to the m by n. R here means these matrices have real valued entries. That's why we use R. And almost everything we will use here does have real valued entries, though I should say when we get to power systems, we will have some complex valued entries too. So we can also have a matrix of complex valued elements. We call that C m by n. I'm not as good as writing that C, but it's clearer in my text there. Similarly, a vector we will denote a, and I should say also, by the way, to talk about a certain element of A, we'll use subscript. So Aij would refer to the element in the ith row in the jth column. To talk about vectors, vectors are, in our case, always going to be thought of as column vectors. So they are vector or matrices with many rows and one column. So X and Rn is effectively actually a matrix X and Rn by 1, but we don't write that part. We just assume the vectors are always column vectors. And again, as we've seen already, to refer to the ith element of X, we would say something like Xi. The transpose, which we've already seen, is an operator that switches the rows and columns of a matrix effectively. So for a matrix A in M by N, A transpose would be N by M, and A transpose Ij would be equal to Aj. Now, importantly, for a vector, since we're talking about column vectors, when we talk about a vector, if we want to talk about a row vector, that is a matrix with one row and many columns, we'll use the notation X transpose. So for a vector Xn, right? Sorry, X in Rn, so if X equals this thing, skinny matrix like this, skinny matrix essentially, then X transpose would equal the row vector. Okay? All right? Now, one thing that's sort of important in this class, and this is especially important when we talk about writing things in matrix form, is thinking about a matrix in terms of its rows or in terms of its columns. We'll often want to write it in terms of its rows or in terms of its columns. So, for example, we may take the matrix A and write it in terms of its different columns. So we'll have A1 be the first column, A2 be the second column, all up to AN being the last column. Now, importantly, here, each AI term, AI here, is itself, an M. Each AI term is itself a vector here. In the slide before, when we talked about X being a vector, then Xi represented the ith element of X. Here, AI represents itself a vector. Okay? We did the same things with X's in the machine learning case, right? We said Xi is itself a vector denoting the ith input. Whereas Yi, in some sense, was an element of this big vector of Y, right? Because Yi was a scalar. This can be confusing at first, but you will have to deal with it using this notation. It's just there's no way around it. You will see this being used. People will want, depending, essentially, if you can never do this, notation will get very cumbersome very quickly. And so we really want to be able to use things like AI to denote a vector sometimes, and sometimes an element in a vector. If I do ever want to talk about the jth element of AI, I will use this terminology. I will use AI, put parentheses around it, and then sub j. Okay? But importantly, here, AI is a vector. We can also write a matrix by its rows. That will also be useful to do. So instead of by its columns, we can write it like this. A1 transpose. Remember, we're talking about a row vector now. So we will always use transpose to talk about a row vector. Right? If we want to say A1 transpose is the first row, and A1 is a vector, then A1 transpose is a row vector. A2 transpose, etc. AM transpose. Right? And here, AI is a vector in R to the n. And it's important to know, if I write AI, I mean the column vector AI. If I write AI transpose, I mean the row vector AI transpose. So the other last thing is that these A's are not the same as in the previous slide. Okay? They're not even the same size. These A's here are the rows as vectors. So those are going to be n-dimensional. Right? Look in the previous slide. Now we're talking about the columns as vectors. Those are going to be m-dimensional. So depending on how we write it, you know, the notation here for the row or for the column can actually differ. I mean, sorry, the vector AI, depending on how we write this thing, will actually be a different vector. Now, in the notes, I'm not going to get into this too much here. I'm going to describe a few examples. But in the notes, I'll talk about some ways you can do things like multiply matrices, where it's very useful to be able to write the matrices in different forms. Sometimes write them by columns, sometimes by rows. And it actually leads to different ways of interpreting matrix multiplication, for example. But today I won't talk about that too much, maybe a little bit. Okay, now let's talk about some basic operations for matrices. The most basic, well, not the most basic, but a very basic operation is this addition. If I have two matrices, A, m by n, and B, also m by n. It's important these have to be the same size. It doesn't really make sense to talk about addition. Then A plus B, the ij element there is just equal to the aij element of A plus aij element of B. Okay, so just taking the corresponding elements and adding them up. This, of course, should make it obvious why they have to be the same size, right? If they're not the same size, they don't have corresponding elements. So you can't do it. You can't write something like A plus 2. The sad part is Matlab will let you do that. What it will do is it will add 2 elements to every item of the matrix. And that often is not what you want, incidentally. Sometimes it is, but be careful with that. You can use it in your code if you want to simplify things, but make sure you know what you're doing when you do that. We'll talk in a second about how you could sort of really write this in terms of matrix operations, but for Matlab you can do it simply. But never, ever on like a mathematical derivation or homework, you know, the written part of the homework, write something like this. This is just completely incorrect. They are not the right size. You can't add them up. The next operation is matrix multiplication. And you've probably all seen the formula for this before. You have two matrices A in R m by n, and B in n, I think n by p there. B in R n by p. Then you can form their product. We'll call matrix C, A times B, and C here is going to be m by p. So this is sort of the basic rule of matrix multiplication here. It's very simple. To multiply matrices, and we'll see what this is in a second, but to multiply matrices, the number of rows, sorry, the number of columns in A has to be equal to the number of rows in B. And the resulting size of the matrix is as if you just took away these elements and squished these number of rows in A and number of columns in B. Now the actual definition of this is the following. The ij element of this thing is equal to the sum from k equals 1 to n of aik times bkj. And one way to think about this is the following. Let's write A by its rows, A1 transpose. I'll write like A I transpose, A M transpose. Let's write A by its rows, and B by its columns. B1, Bj is somewhere there, and B P is the last column. What this is saying is that the ij element of C, so this element of C, right here, is equal to the inner product of this row and that column. So you take every element of this row, multiply by the corresponding element of that column. They have to be the same size, by the way. This is sort of why they have to be the same size, right? You need to have a corresponding number of columns here as rows here. You multiply each corresponding element, then add them all up. That's one way of interpreting, by the way, matrix multiplication. There are other ways as well, but this is sort of the most natural way, maybe, from the definition itself. Now, very important. Multiplication is undefined if we don't have this congruence here. You cannot write, if P does not equal M, you cannot write B times A. You can't do that on the homework or in Matlab, by the way. They will both complain. I will complain on the homework, and Matlab will complain when you type it in. It just doesn't make it, I mean, there's no way to do that, right? These do not have corresponding elements. You can't multiply them together. So don't write things like B times A if B and A are not the right size. There is, as with all things, though, there is one exception to this. The one and only one exception to this is that if you are multiplying by a scalar, if A is this matrix here, and say lambda is a scalar value, which is really, remember, a 1 by 1 matrix, it is OK to write lambda times A. That implicitly means we are taking every element of A and scaling it by lambda. This is not a matrix multiplication because we're not really multiplying the rows, or A has m rows, which might not be one row. This is not a valid matrix multiplication here. But it is so common that we'll just let you do it. You can write this more correctly, by the way, but it's kind of cumbersome, and there's just no real need to do that. So this is the one and only one exception. And Matlab will let you do this too. You can multiply a scalar by a matrix. Matlab will be fine. That means always taking every element of that matrix and scaling it. So this is the one time you're allowed to multiply two things together that aren't the same size, or aren't the, not the same size, that aren't congruent sizes. Let's look at a few examples of this, which come up a lot. One of these that comes up a lot is the inner product, which we've seen already, right? So if you have two vectors, x and y, of the same size, they're both in Rn, then this here, x transpose y, is just going to be equal to, and this is exactly the definition we saw before, but this is going to be equal to the sum from I equals 1 to n of xi, yi. Right, and the way to think about this is, remember, x transpose here, x and y are both vectors of the same size. We have two vectors like this. X transpose would be a vector like this then, right? It would be the transpose of that. It would really be a vector in 1 by n. Y here, this is x. Y here is a vector n by 1. And so the size of that product will be equal to just the outer dimensions here, which is 1 by 1, which is a scalar. This is just equal to a scalar value, which is the sum of all the corresponding elements. Another important way to interpret, for example, and this again just follows out of the definition, but it's a little bit not quite as obvious, is that if we have a matrix times a vector, so let's say we have A m by n, and we have x in Rn, then A times x, that's going to be a vector in Rm, right? This is effectively really m by n. This is n by 1. So this is going to be m by 1 or Rm. One way of viewing this, though there are others, is that we take every column of A And we actually form a linear combination of the rows of A, where the coefficients of that linear combination are the elements in X. This is kind of actually different from what I showed you before. Kind of the natural way to do it, as I showed you before, would be to write A by its rows, and then every element of the product here is an inner product of one row and X. That's one interpretation. This other one, which is also very sort of important to have as a very easy intuition, is that this is also equal to the sum from I equals 1 to n of the entire column, AI. Remember, AI is a column, times xi, which is a vector. Sorry, which is a scalar. AI itself is a vector. X is a scalar. This is actually okay. This is not only, this happens to be also a scalar times a matrix, but this is also valid because AI here is actually, well, I won't write it like that, but AI here is actually m by 1. This is 1 by 1. So this is actually also a legitimate matrix operation, but really you can think of it as multiplying by a scalar. So we take every column of A, we scale them by the corresponding element of xi, and then we add them all up. That is also a way to interpret matrix multiplication. It's very important. Some important properties of matrix multiplication. It is associative. I won't write this down, but you can see them on the slide. It is associative. That means A times B times C equals A times B times C. Doesn't matter what order you do them in. So we typically won't write an order at all. We'll just write A, B, C. Doesn't matter what order you do these in. By the way, it actually can matter in terms of the efficiency of the operations. One interesting thing. So say this A here is n by 1. B here is 1 by m. And C is, I'll say m by p. If you multiply this one out, you'll have a big matrix. Has another big matrix. If you multiply this first, you'll have, well, a row vector times another row vector. Sorry, row vector times a column vector. Actually, maybe I'll do something like this, really. I'll say something like D, where D is 1 by n. If you multiply these two together, let me actually just write this out. This is a simpler case. Multiply these together first, then you have a big matrix here. Multiply these together first, you have a scalar. And then you're just scaling this by a constant. So it actually can be more efficient to do them in different orders, but mathematically they're the same thing. It is also distributive. That means A times B plus C equals A times B plus A times C. Again, not always the same number of operations on the computer, but these are equivalent mathematically. Very, very important, though. Unlike scalars, where A times B equals B times A, in matrices, A times B does not equal B times A. In fact, this cannot even make sense sometimes. So let's say that A times B, A here is going to be, this will be a valid product, right? So this will be m by p, sorry, m by n. B will be n by p. So this is a valid product here. Well, this, B times A, does not have the right dimensions to even multiply it together necessarily. So you can't even, this doesn't even make sense to write B times A. However, even when it does make sense to write, say these are all n. So everything here is an n by n, a square matrix. You could multiply this together. That's fine. It's a valid product. It will still, well, I shouldn't say probably, because there are cases where it is equal. It does not have to be equal. And in the cases you will actually deal with, it probably will not be equal. The number of cases where this is actually equal is very, very small. They're very specific. This will typically not hold by some definition of typical. So never, ever write something like this. And never even hope that it'll be true, because it almost never is true. So do not write that. You can prove all sorts of weird things if you assume that. And we don't want to sort of go with hypotheticals like that. And finally, if you have something like like A times B, and you transpose it, this is equal to each term transposed, but then the order switched. So it's equal to B transpose times A transpose. And of course, you can just imagine you have to do that, because if you don't transpose them, if you wrote something like A transpose B transpose, these could possibly not be the same size, the right size to multiply. I mean, more correctly, if you just write out the definition of transposes and multiplication, you'll see this is exactly the case here. But you can see that this is the case here. But you can just see this is obviously false just by the fact that it would not even be the right size. All right, cruising on along. So some special matrices that we'll encounter. One of the most common ones, which we'll see a lot, is the identity matrix. This we'll write as I. And I is a matrix with ones on the diagonal and zeros everywhere else. It is a square matrix with ones on the diagonal and zeros everywhere else. And it has this very nice property that for any A, this could be a vector, it could be a matrix, it can be any, one of these could be 1 that will make it a vector, but for any matrix, A times the identity equals A. Does not change it to multiply the identity. And you can easily verify this is the case by just multiplying that matrix with the rules of matrix multiplication. This also, by the way, equals I times A. As long as it's important to note that these two I's are not the same here. This I has to be n by n, whereas this I, right, because you have to have something that is congruent with those dimensions, whereas this I here has to be m by m. But they're the same, both the identity. It's in both cases a square matrix with one on the diagonal. The zero matrix is another thing we'll use sometimes. It seems pretty useless, but actually it's quite useful to write things compactly. The zero matrix is just a matrix of all zeros. So this is, I guess one of the times where we will sometimes. I'm saying never write something like this. A plus 2. I guess you could write A plus 0. Not that that would be doing very much. But when you write 0, 0 is one of these special characters that can actually be taken to be whatever size you need in our case. This is very useful when we're constructing things like block matrices. By the way, if you want to specify what size it is, you could do something like this. So say A was m by n here. So for this to make sense, 0 here has to also be m by n. So you could say something like 0. You might see this sometimes, 0 n by m by n subscript. Some people write that. Same with I. People might write like I n to denote an n by n identity. Usually, though, this is implicit by the actual way we're using it, and so we just omit that. So usually, it could not be anything but the one size. For example, in this product here, it has to be n by n, so we just leave off any subscript. The zero matrix is very useful when we want to do things like construct block matrices. So if we have some matrices and we want to construct a bigger matrix, to sort of construct a single matrix out of many other small parts of a matrices, we can use a zero, just kind of do this in a simple way. So if we have two matrices A and B here, I won't write this down, but if we have two matrices A and B, and we want to construct a new matrix where we have A in the top left block and B in the bottom right block, we need to have something on the other sides there, and we can just, for example, if they are 0, we can just write 0 there. So this is a block matrix where this block is A, this block is all zeros, this block is zeros, and this block is B. And now, of course, the size of those zeros blocks are defined by the size of these blocks, so we don't have to bother writing it. We know what size they are. We don't have to worry about it. One more exception about a character is what I'll call the all ones vector. So, and this is only a vector usually. It's not a matrix. It's just a vector, though I'll show you how to write a matrix in a second. So 1 can refer to the number 1, or it can refer to a vector of all ones. This is very useful, for example, if you want to take a vector A in Rn, and you want to easily write an expression like the sum from I equals 1 to n of AI. This is just the inner product of A and the all ones vector, so you can write this as 1 transpose A. You know, fewer lines to scribble, right? You don't have to write a sum, you don't have to have an index here, you just write 1 transpose A. Again, the size of this thing is going to be implicit usually. When you write this, this would only make sense as a valid product if, in fact, 1 was a vector in Rn, and so it's OK. And by the way, the reason why these are the only ones allowed, 0 and 1, is because, this is somewhat philosophical, I guess, but you would never write, really, I told you you can scale a matrix A by multiplying it, say, by 2, even though this isn't valid. You would never write 1 times A, because that's just equal to A. And you would never write 0 times A, because that's just equal to 0, or all zeros. So those characters are kind of a little bit free. We don't use them in multiplying that much. So it's OK to use them as vectors. Because here, 1 here has to be a vector. It could not be a scalar. It wouldn't make any sense, right? This is a scalar. You'll probably get a little bit more familiar with that when you see them used in practice. But just don't worry too much. We'll use this notation a little bit throughout the class, but not too much. I'll try to, especially for 1, because it's kind of confusing. 0 is kind of intuitive, but the 1s is kind of confusing. I'll mention this again when we see it. And by the way, this is how you actually can write this equivalent Matlab code. So if you had in Matlab a plus 2, does anyone know how I would write that? Really? Yeah?
A plus 2 times identity matrix.
So in Matlab, this is saying I want to add 2 to every element of that matrix. So this would not be right. Actually, and the reason it's wrong is for a few reasons. First of all, it's only diagonal. There's only ones on the diagonal with the identity. Second of all, the identity is a square matrix. This may not be square. This may not be a valid sum, period. If you sometimes want this, but you might not want that there. So yeah, what would be another way of doing it?
The dot operator, you use dot plus.
So right, so there's no dot plus in MATLAB. That doesn't exist. There's dot times, which is element-wise products, but there's no dot plus.
Oh.
I'm saying MATLAB. If you write this in MATLAB, if you write this, and I'll put a little semicolon there to indicate that I'm in MATLAB.
MATLAB create a matrix,
Mm-hmm.
same sign of A, and they're all field is true.
So MATLAB has a call, for example, like this: 1s, mn, which will create a matrix of 1s. But actually, so my question is different though. My question is, this works in MATLAB. What it does is it takes every matrix of A and adds 2 to it. This, if you do it on the homework, you will get a big X through it, right? Because it is not a valid addition as far as matrices go. These aren't the same size. This is a scalar. This is a matrix. How would you replicate this out in good math form? Yes, do you have an idea?
A plus 2 times 1 transpose 1.
You're so close. A plus 2 times, yes, 1 transpose. OK, so why does this work, right? First of all, this here is a matrix, right? Because it is a vector. This is n by 1. This is 1 by m. I'm not writing sizes, but I know it has to be that size because A is m by n. So this only makes sense that these are the right sizes. It's sort of crazy, right? Because there's actually 2 different sizes here, but you can still write it. So this is a matrix. It's OK to multiply matrix by a scalar. So that's OK. That's our one sort of time we can cheat a little bit. And now these are matrices that are both. Oh, sorry. This is m by 1, 1 by n. It's going to be hard to say that in the video, I guess, but m by 1, 1 by n. And this is m by n. So these are the right sizes. And this will, in fact, be a matrix of all 1s here, because essentially, actually, does everyone get that? What that's matrix of all 1s? So what you have here is you have this matrix, 1, this, times this row vector. And that equals us a rectangular matrix here, where the ith element is this element times that element, which are both 1. So every element here is going to be a 1. So these are just sort of little things that, like, this is actually, it's not that hard, right? But if you haven't seen this before, it's just sort of tricky to get this for a second and see what this is actually doing. So this is the kind of stuff you may see in this course. Again, we'll try to kind of keep it to a minimum here. This is sort of one of these, I didn't intend to ask this, but it just sort of had that idea. So we're not going to quiz you on this kind of stuff, but it's just good to know when you want to sort of think about what's the right way to write certain things, that you can write it in matrix form. It's just that we're not going to typically do it like that. All right, we'll continue this next time, where we'll just pick up with this. We'll hopefully finish through at least the Matlab part as well next time. But then we'll see you on Thursday. Yeah, question.
This is a public service announcement. Matlab takes like an hour to download to do it before class. It's like 4 gigs.
Oh yeah, okay. Yes, you can download for free on the SES. Sorry, not SES, but CMU's software server. But yeah, it's very big. It's also, do you have to apply to get a license key, or is that's pretty quick, right? Okay, it comes with the download for you guys, yeah. So, okay. Yeah.
Size of 1 second.
1 second.